Hello everyone, my name is Alex Bardas, and together with my colleagues from Kansas State University and our collaborators from HP Labs and HP TippingPoint, we've been working on UDP-based distributed denial of service detection. I would prefer to answer your question at the end of my presentation, but if you have a question that cannot wait, please go ahead and ask it, and I will try to address it. Okay, probably most of us have read or heard about different attacks that a group of hackers named Anonymous, or hacktivists, the way they're calling them, have launched against different important companies' websites and servers and government websites, or different other servers because of different reasons. They've been using the low orbit ion cannon. This was one of the tools that was mentioned in most of the articles that were published about these denial of service attacks. And they were just pretty much flooding these websites unusable and creating a lot of damage. So when we think usually about DOS and DDoS, most people probably think about TCP. However, I will talk today about UDP-based DOS and DDoS attacks. Why UDP-based? Answer is simple, because reportedly in the last 2 years, all these distributed denial of service attacks, or a significant part of the traffic was UDP traffic. Also, there's one more important reason, the fact that launching a denial of service attack, and especially a flooding attack, is very easily nowadays. There's tools out there that are available and can be downloaded by users and just launched against different websites. There are a lot of videos on YouTube where you can see how people use Loai in a very funny way by flooding their school websites or companies' websites. They have no idea what they're doing, but they're using the tool. However, despite past research, we still lack practical solutions to deal with UDP, DOS, and DDoS attacks. Some of the previous DDoS methodologies for handling DOS and DDoS traffic they apply to UDP, but there's a lack of understanding on whether key assumptions made in these works really hold for UDP traffic. Very little, if at all, work has been done that tries to understand the UDP traffic characteristics in production networks. Because of the fact that we had access to 12 different data sets from 12 distinct networks, we focused our efforts on understanding these UDP characteristics in real-world networks, real-world data sets. So, in general, the user datagram protocol. UDP is a transfer protocol that offers minimal transport service. A UDP packet has a header and a payload. The header doesn't have, unfortunately, too much information. There are only 4 fields: source port, destination port, length, and checksum. 2 of these fields, the source port and the checksum, are optional. So we'll have pretty much three characteristics to look at: destination port, length, and payload. UDP does not provide reliability, datagram ordering, or data integrity. So no reliability means no acknowledgement packets, and an application program running over UDP must deal directly with end-to-end communications problems, problems that a connection-oriented protocol would have handled. Okay, some of the UDP DOS and DDoS characteristics that we could see in all traffic generated by the different flooding tools. So if we looked at the packets, and usually every packet has the same payload, the source IP address may or may not be spoofed. Recent attacks have shown that if it's not spoofed, or at least if it's not randomized, the source IP address, then the attack has more chances to be effective. And if we're sniffing the network and flooding attacks, UDP flooding attacks is going on, we can observe one-way flood of packets. So, okay, if it's the same payload, does this mean that the same payload can count as a stable DOS and DDoS feature, detection feature? Oh, well, nah, it's not really the case. We looked at Loai and we were able to modify the source code so that we were generating a unique payload for every single packet that Loai was generating and sending. And we were generating the payloads on the fly, and Loai was still effective. It was pretty much sending at half of the speed of the original version. However, this problem, the speed problem, could have been circumvented if we would have had pre-computed the payloads. On the other hand, the replay attacks, we would say that unique payloads, they look different than uniquely generated payloads. They look different from benign UDP application payloads. However, what about replay attacks? An attacker can generate, UDP traffic with the benign application and use this traffic and send this traffic towards target at a higher speed. The other big challenge when it comes to detecting UDP flooding attacks is the fact that UDP is stateless. So DOS and DDoS prevention methods based on connection state are not applicable in this case. Therefore, we had to look for something different and turned at the proportional packet rate assumption that says that during normal operation, the packet rate of traffic going to an address is proportional to the packet rate of traffic going from that address. Obviously, this applies to TCP by protocol specification. But what about UDP? Even though the protocol specification does not require an acknowledgement message or a confirmation message, at the application layer, UDP benign applications have to have, they are implementing a mechanism that makes sure that the other party is still live and or receive the sent packets. We would like to have dialogues on the internet, right? Or if there is a monologue, just a one-way communication, then it should be short. It should not go on for a long time, right? That's pretty much the intuition when we're thinking about benign traffic. Therefore, we hypothesized that under normal operation, the ratio will be less than a predefined allowed maximum threshold value, and that the ratio can be used to separate benign traffic from attack traffic. So we were expecting, so our intuition was that, for instance, for every n packets that the source sends, there will be a confirmation packet or something like this. Okay, and our next step was to develop a classifier based on this proportionality assumptions, because we thought that we can detect early at the victim side DDoS and DOS attacks by calculating the ratios for every single sender. Our classifier monitors an enterprise network and tries to detect possible DDoS flooding attacks targeted at it. Of course, approaches that need global cooperation on the infrastructure level from different ISPs or autonomous systems, they're very attractive, but they require significant efforts and in deployment and coordination. Therefore, our approach has an important advantage from the practical perspective, because the owner of the enterprise network has the sole authority to deploy this protection, and because the owner is the main beneficiary of it and also the main victim of the collateral damage, we have strong reasons to believe that this is it's highly likely to happen. Okay, so our basic approach, I summarize this here using this diagram. So pretty much our monitor destination can be one host or can be a network, enterprise network. For every single source IP address that it's communicating with, we named it a bucket, that stores the number of incoming packets and the number of outgoing packets to this address. And we are using a sampling approach, so we will have a validation of certain time that this bucket will be alive. If it expires, then the counters will be, and the communication between the source IP address and the monitored destination still goes on, the counters will be reset to 0. If not, then the bucket will be deleted. However, if we have a bucket, a valid bucket, then we are calculating the ratio by, the ratio will be calculated by dividing the number of incoming packets by the number of outgoing packets. Of course, if the outgoing packets, they're different from the number of outgoing packets is different from 0. And if it's not the case, then the ratio will be equal to the number of incoming packets. After calculating the ratio, every time a packet arrives or it's sent to this source IP address, we'll test if the ratio is greater or equal to the threshold value. If it is, then we're issuing an alert. If not, then it's pretty much fine. So we are doing this for every single source IP address that our monitored destination communicates with. Our classifier has to see all traffic. We have to avoid asymmetric routes. If this is the case, then we'll have to have a mechanism so the classifier knows about all the traffic. Otherwise, this approach might not be accurate. So we tried in our experimentation part, we tried to validate our hypotheses by measuring the ratio for benign and for attack traffic, and we measured the ratio on synthetic data and data from production networks. The synthetic data was, part of it was generated on our own testbed at Kansas State University, and the other part on DETER lab. And production networks, we had data from our departmental network. We sniffed the traffic for several weeks, and we analyzed this traffic. And then we were fortunate to get some data from industry, some non-DNS UDP packet captures from the 12 distinct networks. The Argus Cybersecurity Lab contains a network of 20 plus physical hosts. We use various UDP protocols and applications from DNS, NFS, DHCP, NTP to instant messenger applications like QQ, MSN, or different video streaming applications like Sopcast or PP Live, and different games like Counter-Strike, or networking games, Counter-Strike or Quake 3 that are using UDP. We put all these applications on our testbed and measured the benign ratios. We also used primarily Loai on our network to generate attack traffic and see if there's a difference between the ratios. On DETER lab, we created, this is the setup that we use. We pretty much try to mimic our CIS network from our department. So we had two local area networks connected to a border router, a Windows local area network that contains only Windows machines, and one that contains only Linux machine. And then the border router was connected to 3 external sources. Excuse me. We used the security experimentation environment, SEER, to generate benign traffic, and of course, and Loai primarily to generate flooding traffic on DETER. In our department, we were lucky to get a span link where we were able to deploy a server, a machine that was running our DDoS detection tool, and our tool was reporting suspicious source addresses. We've been doing this for a few weeks. But the data that you will see, the results that I'll talk about today, they're approximately from 6 days that we thought that they're more descriptive. And the 12 distinct networks that we were kind of bragging about and talking, this data is from large corporations, edge and core ISPs, universities, and financial institutions. For privacy reasons, DNS traffic was removed and the names of the networks cannot be revealed. But the data was captured between 2002 and 2012. The number of flows varies from a few hundreds to hundreds of thousands, and the duration of the data set is between 1 second to a few days. Experimenting a DDoS methodology on real network topologies is extremely challenging because in part of the fact that data sharing is actively discouraged by commercial solutions and also for privacy reasons. So we were very happy that we were able to get this data. So these are some of our results. So for instance, we chose a sampling time, a bucket time to live of 3 seconds, and we can see that the ratios for benign traffic, they're from less than 100 on our testbed to a few hundreds, or to even more than 1,000. This is because this data set from the production networks that we named D contains one-way protocols like syslog over UDP or NetFlow, older versions of NetFlow over UDP. So therefore, the ratio was a little higher. If we're looking at one data set, usually we can see that if the sampling time increases, the ratio also increases, but this is not always the case. For instance, on this data set, ISP that I will talk about I'll talk more about in a few slides later. The ratio is pretty constant. Okay, this is we can see that the ratios are in the hundreds, especially for short sampling times. For huge sampling times, they can go up to a few thousands or even 20,000 in this data set named O that contains some one-way protocols as well. The attack traffic ratios. For instance, this is after 4 seconds time into the attack. We used a short bucket time to live, a short sampling time of 3 seconds. We can see that at the high speed, the ratio is in the hundreds of thousands. And usually, attackers will have to go with higher speed because if they will use lower speed, the lowest speed or lower speeds, then and their traffic is not distinguishable from the benign ratios ratios that benign traffic is also producing, then the attacker will have to generate a lot of resources. So this is pretty much what we are trying to do. We're trying to make their it's an arms race. So we are trying to make their life harder and make them use as many resources as possible. For instance, on a lab machine, an i3 machine with 4 gigs of RAM, we were running a web server and needed around 900,000 UDP packets per second to render that web server unusable. So think about how many machines an attacker would use just for a simple desktop machine if he will go with the lowest speed. Of course, if their bot armies are really huge, then there might be some problems. Okay, our results analysis. So we concluded that benign applications. We observed that benign applications use UDP traffic in different ways. There can be a constant communication between the sender and receivers. Some examples are NFS over UDP or video streaming applications like Softcast. Then there might be benign applications that have an initial communication, then a one-way burst of UDP packets follows. Some examples are SIP and a fax protocol. And then there are other protocols that by design no response message is necessary, so there's just a one-way burst of packets. Example, syslog over UDP and NetFlow, older versions of NetFlow. Even if we have to deal with one-way bursts of packets, still the individual ratios for these applications these applications will generate, it's lower than what flooding applications will do. So we cannot, under normal operation, the ratio will be less than a predefined maximum value. We think that our hypotheses hold if the cutoff pair values, like the maximum threshold value and the BTTL, are correctly chosen. So there's no silver bullet. We have to measure the benign UDP traffic ratios on the target network before tuning the classifier. There are no values that could work for all cases, and it's pretty risky to do that. And that's what we did in case of the ISP dataset. This dataset was from the last week in January 2012, so 3 months ago. And the dataset owner, they confirmed that, and they told us that we just reported suspicious traffic, and they told us that they're positive that it's a DDoS attempt. So the benign ratio was usually approximately 85. We discovered that 2 addresses were sending during 2 minutes they first started sending with very low ratios, but then it increased to 300 and something, so way more than 85. And after we discovered these 2 addresses, we looked closer at the traffic that they were sending, and it looked like flooding traffic, because probably generated with an application similar to Loai. So payloads were the same, and source port was randomized, looked as being randomized, and destination port, probably they said it was 80, so most probably they went for something well known, so firewalls will let it through. Some limitations and future work: spoofed, especially randomized IP addresses and NAT setups can cause problems for the classifier. However, randomizing IP addresses might be a bigger problem for the attacker, because most ISPs are performing egress filtering nowadays. And we are working now on the inline version of the classifier. This will have a new feature. It will try to interact with the source by blocking for short times the incoming packets, or by filtering them for a short time. This version is under development, and we hope that we will be able to deploy it in a number of production networks. We have some customers that our collaborators work with that are willing to let us put this into place. So in conclusion, we designed a UDP traffic classification algorithm based on the proportional packet rate assumption. The proportionality assumption was examined through experimentation on a large number of data sets from production networks and various test beds, and we believe that our experimentation results provide key observations for DOS and DDoS detection. Thank you very much. Please let me know if you have any questions.
Hi, nice talk. Question on the actual algorithm. You use the bucket, you use the source IP is the bucketing strategy. So where is the actual UDP port number is used? If you're using a source IP, then it could be used for any kind of IP application, not necessarily TCP like ICMP, anything can be bucketized. So what is so specific about UDP here?
I don't really think I understand your question. What do you mean by what is so specific?
Because the buckets are used on source IP based on
Yes.
threshold values. So source IP is an IP header. So where is the port number of the UDP is used here?
The port number is not used.
It's not used. So
No.
it can be used for the ICMP packets or any flood kind of.
Yeah, it could be for ICMP, yeah.
Another question that I have, did you mentioned like the IceCast streaming server that you tried?
Which one?
Something to stream media over the network. It's
Oh,
basically
yeah.
my question. So I assume there you would see at max like 1 packet for a request, and then you would see the stream flooding, because at a certain point the server doesn't care whether the client is still alive, especially if you're talking about multicast, for example.
I was seeing I looked at specifically at this PP Live and Sobcast, and usually the rates were for every 10 packets that the source was sending, there was a confirmation packet. And the confirmation packet had the same payload every confirmation packet. So it was around 10 every 10. I was a little surprised, because on our testbed, when I looked at, and my colleagues at every single benign application first in isolation, The rates were very low. But when we put them together, they went to more than in the hundreds, and we did not really expect that first.
I like your metric because it seems pretty simple to use and pretty quick, but it seems to require a global view of the network and no sampling, basically. So you have to see every in- and outbound packet. Is that correct?
Yes, that's correct. Asymmetric routes might be a problem. And we had a few data sets. We did not put them, I did not add them to this presentation because the results were not really relevant, where we had to deal with asymmetric routes. For instance, we had NFS traffic, NFS over UDP, and we could see all requests, but we couldn't see the responses. And then there's another data set where we had SNMP, and we could see the responses, but we couldn't see the requests. So, and it was confirmed, the datasets providers, they told us, yes, these are affected by asymmetric routes. So even though in our paper we've put the results there, even with asymmetric routes, the ratios were around 10,000, something like this, but not hundreds of thousands or, so high.
I'd be interested to see some extension of this work proposing coordination between hosts that see portions of network traffic.
We are trying to deploy it in some real networks for now, and then depending on how if it looks promising, then of course we are looking into extending it and synchronization mechanism between the different instances of the classifier. Because usually now we went to a sequence of classifiers, so the attacker cannot adapt to our rates. We have different rates in, it's a sequence of classifier monitoring pretty much the same target, same asset.
Thank you.
All right, we're running a little late. Let's do 2 more quick questions as the people already lined up, and then I would ask Armin to set up his laptop.
Hi.
Hey.
Thanks for the talk first. My
You're
name is
welcome.
Yazan Bushmaf, University of British Columbia. So how do you exactly calculate the maximum threshold?
Depending, you're measuring, first see what benign applications, UDP applications, are pretty much running on your network. And here we had an instance of the classifier that was just measuring the maximum benign ratio that is encountered. Based on that, you are choosing your maximum threshold.
So you actually learn this value?
Yes, you have to. Yes, you have to make some measurements in order to determine this value. There's no silver bullet that works for everything. You could find one, but it's not really what we are.
My concern is that,
Excuse me.
machine learning based detection techniques are, they have their security problems. For example, the boiling frog attack, I don't know if you're aware of it, where the adversary starts introducing gradual abnormalities, and at the end your classifier fails at detecting the large-scale attack.
We can discuss more about this offline. Yeah, there's some challenges that just measuring once the ratio, it's probably not precise. And as you said, it might be, you have to depending on the network that you're monitoring, you have to take this into account as well. Yeah.
Thank you.
Sure.
Just very quick, if I see 2 people communicating, for instance, voice over IP, can I spoof one's IP address and then have you take down the communication?
You mean
so if I spoof one of the parties involved in the communication, then your system will actually take down their communication, right?
If you're spoofing, yes. If, for instance, you're spoofing your neighbor's address and you have the same ISP, and probably will take your neighbor's addresses down. Okay, thank you very much.